These are the Math 105A Chapter 5 notes. Chapter 5 will cover factoring, and I want you to think of factoring as the opposite of the distributive property, which is what we learned and talked about in Chapter 4. So just like many operations in math are opposite of each other, such as multiplication and division are opposite, addition and subtraction are opposite, factoring and the distributive property are opposite. So we want to go through several different types of factoring techniques throughout the next several sections. The first technique that we're going to talk about is called the greatest common factor, and often we refer to that as a shortcut as the GCF. So in case you hear me abbreviate that, the GCF. So the GCF involves finding the greatest common factor in each term and factoring it out. Okay, so before we look at problem 1, I just want to back up and review what we covered in chapter 4. So for example, if I gave you 8 times parentheses x plus 3 and we use the distributive property, we would distribute the 8 to get 8x plus 24. So this direction was chapter 4. What we'll be working on now is going in this direction, which is chapter 5. Okay, so we'll be looking at this end result and asking ourselves, is there a number that divides evenly into 8 and 24? That's 8. And if there were variables in each, is a variable appear in each term? And if so, we can factor that out. So that's the idea, that we want to reverse the process of the distributive property. And what's great about factoring is that we can always then distribute again to get back to the original problem and check ourselves. Okay, so as you'll see, example 1, part A is very similar to what we just talked about. If we're only considering the constants or the coefficients, we want to look at 8 and 24 and ask ourselves, is there a number that divides evenly into both? And that number is 8. And then we want to say, okay, well, these are like mini division problems. So factoring is very similar to division, where we're going to take the value that we factored out and create these little division problems, and their results are what goes in the parentheses. And then again, we can check them. So this is our final answer here. But what's great about factoring is we could always check it and distribute. And we do that and we get 8x plus 24. So that's our check that we got back to the original and that it all checked out. Okay. In the second problem, we see that we have a negative up front. So anytime we have a negative along with the coefficient, we want to consider factoring that out. So I'm first going to look at 5 and 10, and the number that divides evenly into both of them is 5. But because that leading term has a negative, I want to take that negative with it. We also notice we have a y squared and a y. So if a variable appears in every single term, then we can factor one out, and we want to take the exponent that is the least. So we see this as y to the first and y squared. Y to the first is the least, so I will take that out. And then I'm going to set up my parentheses. And again, we can think of this as mini division problems, where I would be dividing each term by what I just factored out and working through that. So the negatives cancel, the 5's canceled, y squared over y is y. Negative 10y over negative 5y would be positive 2. So watch the signs. Okay. And again, if you wanted to distribute to check it and make sure it works, negative 5y times y would be minus 5y squared. Minus 5y times a positive 2 would be minus 10y. And we can see that that is the value, that is the expression that was given to us first in the original problem. So always use that distributive property to check and make sure we get back. We won't check all of them, but it is a nice check to be able to confirm our factoring is correct. Let's move on to part C. Looking at 16 and negative 24, looking for a number that divides evenly into both of them. When I look at 16 and 24, I think about factors of 8, so an 8 will factor out. And then I'm looking at the a's. A variable appears in both, so I'm going to take an a, and the lowest exponent under consideration is the 2, so that is my GCF. 8a squared is my GCF. And then I'm setting up these mini division problems and working them through. You don't always have to write this out, but it's good practice until you get the technique down. And then we're working these through. 16 divided by 8 is 2. 8 to the 4th divided by a squared is a squared minus 3. So you'll see all those rules that we learned in chapter 4 about how to handle the exponents for the quotient rule. They're coming in handy now. And again, you could take this and distribute it out and make sure you get back to the original. Part D, our last one, this is pretty involved. We see lots of x and y's here. So this is 4 terms, and we're just going to go one term at a time. We're going to ask ourselves, is there an x in every single term? There is. Is there a y in every single term? There is. So now let's look at the exponents. The lowest exponent on the x's under consideration is 2. Same with the y. So I'm going to set up my parentheses, and again I'm thinking of these as dividing every single term by what I just factored out. So if it's helpful to you to write this out, please do so. And then we're working through all these mini problems. So let's see, 2 x's cancel, I'm left with 3, and the same thing with the y, it's a cubed. Next term I have x squared and a y. Third term, I have an x and a y. Notice what happens in the last term. Every single thing cancels. The 2 x's cancel, the 2 y's cancel. Don't forget to still represent that term. You're left with a 1. Okay, so that 1 does have to hold the position. We don't want to completely cancel everything out. So this first technique is called greatest common factor. Okay, so continuing along with the idea of finding the greatest common factor, if we looked at some of the problems that we'll be working on, the greatest common factor doesn't always work. So on the last 4 problems it did, but when we start moving into problems with 4 terms, we're actually going to have to use a new technique that involves the greatest common factor, and it's called factor by grouping. And we're kind of going to phase into this. So the first thing I want you to think of is that when we factor out the greatest common factor, it can be a single variable, it could be a number, or it could be a grouping of numbers. So when you look at this first problem, I want you to look closely at these parentheses. So I don't want you to think about distributing. I want you to recognize that what I've highlighted here is actually the greatest common factor. It's what's in common to each term. So I'm going to factor out that x plus 3. And again, setting up these mini division problems. And as you get better at this, you won't always have to write this out. Now we're going to look at what's left. So the parentheses, remember, if we set up these mini division problems, the x plus 3's cancel. I'm left with x squared. The x plus 3's cancel. I'm left with minus 7. So this is still using that technique of a greatest common factor, the way the problem was presented in part A. But now I'd like to go to part B. So part B has 4 terms, and if we look at the problem we did ahead, let's see, part D above, that had 4 terms, because it had a greatest common factor. But when we look left to right, first thing I want to ask myself, is there an x in every single term? And when I get to the 21, I have to say, no, there's not. There's only in the first three terms. So then I look to see, is there a 3 or a 7 or a factor of 21 that's in every single term? And again, there's not, only in 2 of the terms or 3 of the terms, but not all 4. So when we have a 4-term polynomial and we cannot find a greatest common factor, then we're going to take the approach of factor by grouping. So factor by grouping says that we can split it into groups and then use the approach of greatest common factor again. So that's what I'm going to do. I'm going to group the first 2 terms together and the last 2 terms together. Okay, so looking at the first 2 terms, I'm going to take the approach of GCF again. Is there a greatest common factor? I don't see a number that's a factor, but I certainly see x in each, and I actually see x squared. So I'm going to take out x squared, which would leave me with x plus 3. Now again, how did I get that x plus 3? I'm dividing each term by x squared. I didn't write it out this time, but x cubed divided by x squared is where I get my x. 3x squared divided by x squared gives me a 3. Okay, and then I'm going to look at the 7x plus 21 separately, ask myself what would the GCF be, and I see that 7 divides evenly into itself and 21, so I'm going to factor the 7. Divide each term by 7, and I'm going to get x plus 3. Now notice what we've done is actually created a common factor. So this is the step that allows us to go that next step and factor out that x plus 3. Again, we're not going to write it out, but if we divide it by x plus 3, it would cancel, and I'd be left with the x squared in the first term and the 7 in the second term. So you can kind of see when you factor out this x plus 3, you're regrouping these terms here. Okay, so let's try that technique on parts C and D. So I look at the 4 terms and I ask myself, is there a greatest common factor in all 4 terms? So I see an x in the first 3 terms, but not the last one. And I also don't see a number that would divide evenly into 4 terms. So this is where I'm going to factor by grouping the first 2 and the last 2. And then same approach, find the GCF. So 7x cubed, 5x squared, 7 and 5, neither one of them have like factors, but I can factor out an x squared. Divide each term by x squared, I'm left with 7x plus 5. Now I'm going to look at the last 2 terms, and again, 21 and 15. What divides evenly into both of those? I think that would probably be a 3, but because my leading term has a negative, I'm going to take that negative with it. So minus 3, divide each term, negative 21 divided by negative 3 is 7x. Minus 15 divided by negative 3 is plus 5. So again, notice what we did is we created this common term. So this technique requires that you have this common term pop out. If it didn't happen, you want to back up and reevaluate your factoring. So what's in highlighted yellow gets factored out. So this is 7x plus 5. And then we're regrouping what's out front, so the x squared minus 3. And again, a check of this is that you would use the distributive property. So if you distributed all 4 of these terms, you should get right back here to what you started with. So that's a very good check. Okay, part D, same approach. I'm looking at all 4 terms. I do not see a GCF among any of them, so that's where I'm going to take the approach to group by 2 and 2. 9 and 6, I can factor a 3 out. I have an n in both, and the lowest exponent is 2. I'm dividing each two terms by 3n squared. So 9 divided by 3 is 3, n cubed divided by n squared is n. 6 divided by 3 is minus 2, and the n squareds cancel. Okay. When I look at my last two terms, I don't see any variable that I can factor out, and I actually don't see any constant that I can factor out either. So I'm really just going to group these together. And when I do that, I notice that even without factoring anything out of the second term, I've created that common factor. I do want to go back and really think about what is the number that's in front. Remember, even though nothing is written there, it is a 1, so that's going to help me when I pull together my factors, remembering that that 1 is there. So it's highlighted in yellow, comes out, factored, and then I'm regrouping the rest. So the 3n squared comes down, and don't forget the 1. The 1 is there. Okay. So again, you could check this by using the distributive property or the FOIL method, however you remember it. And if you did it correctly, you should get right back to the original. It doesn't matter if the terms were in a different order, they are still equivalent. So if you factored that and got different order, that is still correct. Okay, so we've learned two techniques so far. We've learned about greatest common factor and factor by grouping, which uses it. We're going to go on to use several other techniques, but it's an important point to point out that anytime you do factor, we might have multiple techniques that we're using, but GCF should always be your first attempt. Okay, so even if there are other methods that we will apply as we work through some of these problems, first thing we will always look for is a GCF. The next factoring technique we're going to be talking about is factoring a trinomial. So a trinomial is a polynomial with 3 terms, and we're going to specifically be looking at the type that is x squared plus bx plus c, noting that the coefficient in front of the x squared is 1. So this is a specific type and a specific approach that we will take to be able to factor. Okay, a couple things that we want to cover first is we kind of have a set of guidelines for the rules on how to determine some of the signs that we're going to use. First thing we'll say that if you have a trinomial that factors, it will always factor into 2 binomials. So what's a binomial? Binomial has 2 terms. So tri has 3 and a binomial has 2. So that means we're going to have 2 smaller polynomials that have 2 terms, and they'll either have a plus or a minus in between. So we're going to talk about some of the guidelines for determining when we'll have positive or negatives inside our binomials, and it will all be based on C. So when we talk about C, C is the constant that stands alone. B is the constant on the X term, and then eventually we'll talk about having an A here, but for now it's a 1 in front of our X squared. So C can be positive or negative. When C is positive, both of the factors of the binomials will have the same sign. So if C is positive, both factors will have the same sign. If C is negative, there'll be one factor that's positive and one factor that's negative. Okay. When we're done, once again, we can use the FOIL method or the distributive property as we know it to check our answer. So let's use our guidelines here and let's work through some of the possibilities of determining what the factors should be. So again, we've said that we have a trinomial, and a trinomial factors into 2 binomials. And now is a good time to kind of step aside and talk about, remember what we did in chapter 4 with the distributive property. So if we go to the side here, and I'm going to give you a problem such as x plus 4 times x plus 2. And remember, we learned with the distributive property that we're going to have all 4 combinations. X times x is x squared, x times 2 is 2x, 4 times x is 4x plus 8. And then our middle terms combine together to give us 6x plus 8. Okay, so this is an example of chapter 4 headed down in this direction, and what we want to do is go backwards. So chapter 5 starts at the x squared plus 6x plus 8 and says, okay, I want you to write the factors as two binomials. Okay. So now that we saw that process, let's think about what we should do in the given problem. And we know that we have 4 positions, and this is often referred to as FOIL. So the firsts multiplied together, the outer positions multiplied together, the inner positions multiplied together, and then the lasts. So let's think about this. If we have 2 binomials, we know that the x and x must take on the first positions. And then we also know that the 16 must come from the last positions. So what we want to do is go to the side and think about all factors of 16. So 1 times 16 is 16. 2 times 8 is 16. And 4 times 4 is 16. Okay, so that's how we come up with 16, but then we also need to know how do we sum them together. So when we say sum, we are thinking about add. So because the 16 is an add, we're going to add these numbers together. So we have 2 sets of numbers, the combination that multiplies together to give me the 16, and the combination that adds together, that sums together to give me the 8. So the 8 is the middle term that we'll be working on. So I'm trying to match up this with this column. So I can see I have the 8, which means my factors must be 4 and 4. So we found our factors, now we have to work on the sign. So when we go up to our chart here, it says if C, that's our 16, is positive, then both factors will have the same sign, whatever the B is, which is our 8, which means they must be 4 and a 4. Okay, so our 2 factors are x plus 4 and x plus 4. We do notice that they're their exact same factors, so I'm going to take it one step further. And I'm going to write that as a square. Okay, so this factoring of a trinomial is a little bit more involved, but we can again check it by writing out the factors, distributing, combining like terms, and getting back to the original problem. Okay, so let's look at problem part B now. Same process. We have 3 terms. We know we're going to factor into 2 binomials. We know that the first terms have to come from a b and a b to give us the b squared. I'm thinking about all my factors of 4, so I go to the side, I write out all my factors, 1 times 4 and 2 times 2. I then have to think about adding those factors together as well. So 1 plus 4 is 5, and 2 plus 2 is 4. And I'm looking to match the 5. So there's my match. I know my factors must be 1 and 4. And now I have to work on the signs, because notice with this one, I have a negative on the 5. Okay, but I still have a positive on the 4. So remember, this C they're referring to is the last position. Okay, so my 4 is a positive, therefore the factors will be the same, and they will be the sign that is on the 5, which is a negative. Okay. So if we wanted to, we can check it, we can distribute it out, we can distribute the b and the -1, or we can think about FOIL helps us here. So remember, FOIL represents the first positions multiplied together, which is b squared. The outer position, -4b. The inner position, -1b. The last positions, -1, -4 is a +4. And I know I have like terms here, which would be b squared minus 5b plus 4. So there's my check that I get back to the original that I factored it correctly. Okay, so use that anytime you doubt your factoring or need to check it. C, same approach, except now it looks a little bit different. Notice that the factoring format we've been working on always had an x squared and an x and then a constant that stood alone. And now this looks a little bit different. So we want to think about what we learned in the last section that said our first factoring technique should always be the GCF. So I'm first going to take a GCF out of this problem. I know an x appears in every single term. So I'm going to factor in x. We also have that guideline that says anytime you have a negative in the leading term, take the negative. So I'm going to factor a negative x. When I do that, I divide it out of each term. This would give me x squared minus 6x minus 16. Okay. So now I have something that resembles the format in this section that we're talking about. So this format has the x squared plus bx plus c. So I'm going to focus on what's highlighted in yellow and factoring the trinomial into the two binomials. We know the first positions come from the x and the x. I'm thinking about all factors of 16. 1 times 16, 2 times 8, 4 times 4. This time, instead of adding them together, I'm going to subtract them because of this sign right here. So the difference between 1 and 16 is 15, between 2 and 8 is 6, 4 and 4 is 0. And I'm looking to match the number in the middle, which is negative 6x. So I look for my 6, it's right there. I know my factors must be 2 and 8. The sign on the 16 is negative. So if we go up to our guidelines here, it says if the c is negative, one factor is positive and one factor is negative. The larger value has the same sign as b. Okay, so one's positive, one's negative. I look at my b. My b is 6. So I'm going to put the negative, I'm going to match it with the larger number. So that means the negative is going to go with the 8, which means the opposite must be the 2. I'm not going to forget that I factored out a negative x. This does come down and is part of the final answer in this problem. Okay, so this was an example with the C having a negative. We have another one in part D here. The C has a negative. First thing we're going to do is look at all three terms, ask ourselves, is there a greatest common factor? I do not see one, so I'm going to proceed to set up my two binomials. I know I'm going to start with an x and an x. I'm thinking of all factors of 15. So 1 times 15 and 3 times 5. Because this is a negative, I'm going to be subtracting them. I get 14 and 2. I'm looking to that middle number to try to be able to match that. So my middle number, I'm looking for a negative 5, actually just a 5, and I do not see it. So here's a situation where we've gone through the process and we don't have a match. Okay, so when we don't have a match, that means that this problem does not factor and match the negative 5. So the same term we're going to use to describe numbers that don't factor. These are polynomials that don't factor. So this is known as prime. So this does not factor. We have to go through the process and look at all the possibilities before we can determine that. Okay. Last two problems, looking at part E, it does have three terms. It has an x squared and an x, but notice something is different from the format that we learned about. If we go to the top of the page, it should be an x squared first, and then an x, and then a constant that stands alone. So when we look at this, we see this is out of order. It's not in descending order. So the first thing I'm going to do is rearrange the order so I know it works out, and our technique will work. Okay, so now I'm in a position to be able to set up for the two binomials. I'm going to have an x and an x, and I'm working through all the factors of 72. There's a lot of them. Okay, and you could write them all out. 1 and 72, 2 and 36, 3 and 24, 4 and 18, and you can keep on listing these. You don't have to write them out every single time. What we're looking for are factors that multiply to give us 72, but whose difference, and why do I say difference? Because it's a negative, but whose difference is 6. Okay, so if you work through all of these, you should find that that factor is 12 and 6. So 12 times 6 is 72, but if we subtract 12 from 6, we get 6. So those are the two conditions we're trying to meet. We also see that they are a negative on the 72, so they're going to be opposite in sign. I look at the 6, and I always take the sign on the x, so that's a plus, and put it with the bigger number, which means the other one must be opposite. Again, you could always check your factoring by foiling, distributing out, and making sure you get back to the original problem. Okay. Last problem, I see a negative in front, so right off the bat, I think I want to factor out the GCF. I'm going to look at 4, 40, and 100. They all divide by 4, so I'm factoring a negative 4 out. And then I'm just working on what's in the parentheses. It fits the format of x squared plus bx plus c. So I'm setting up all my factors. I'm going to have an x and an x. I'm going to keep this negative 4 out front. I'm looking for all factors of 25, so two numbers that multiply to be 25 but add to be 10. So that's going to be 5 and 5, and if it took you some time to write out the factors like we've done in previous problems and work it through, that's perfectly fine, especially if it's your first time learning factoring. Okay, so I have my factors. Now I have to look. The rules say if my 25 is a positive, and it is, then the factors will be the same sign. Look to the 10. So they're both going to be plus and plus. The last thing I want to do is observe that both of my factors are the same. So remember, when we have factors that repeat each other, we do want to write them with an exponent. This is considered the most simplified form. In our next technique of factoring, we'll be working on factoring trinomials of the type ax squared plus bx plus c. So in our trinomial, instead of having a 1 in the a position, we will have a different value. So not only do we have to consider all the factors of 4, we're going to consider the factors of the product of 2 and 4. So I'm going to take these two numbers and multiply them together to give me an 8. And now I'm going to consider all the factors of 8. So if I branch this out, I have 1 and I have 8. And then I also have 2 and 4. We're going to follow the same guidelines that if the 4 has a negative, we're going to subtract these numbers. So the difference between 1 and 8 is 7, and the difference between 2 and 4 is 2. And I'm looking to match the 7. So I know my factors should be 1 and 8. So what I'm going to do now is I'm going to take the 7x and I'm going to use that I found, and I'm going to rewrite the 7x. So I'm going to keep the 2x squared. So I have 2x squared, and I'm going to keep the minus 4, and I'm going to rewrite the 7x as 1x and 8x. And I have to make sure I get the signs correctly. Remember, the rules we learned in the last section said that if it's a negative on the C, that the sign should be opposite, and I should end up with a plus 7x. So that plus is going to go with the largest factor, which means the second factor would be the negative. And you can check that. 8x minus 1x equals 7x. Okay? So we rewrote these two factors to be able to have two terms that combine together to give us that 7x. Okay, so now when we look at this problem, this should look very similar to our technique of factoring by grouping with four terms. So now I'm going to approach this as factor by grouping, and you're going to see it becomes a much easier problem to factor. So if I look at 2x squared plus 8x and I find the greatest common factor, I would factor out a 2x and I'd be left with x plus 4. And in my next two terms, I have a negative, so I'm going to pull the negative. But when I look at it closely, I really don't have anything else that I can factor out. So I'm going to pull just a -1, and that would give me an x plus 4. So notice what we're looking for in factor by grouping is this common term. And we do see this here. So now I can pull that common factor out of x plus 4. And then I'm going to regroup the two terms that are left over to x minus 1. And we have factored the trinomial of the form ax squared plus bx plus c. So again, if you're unsure of this and you want to check it, we can use our distributive property where we can work this out and we will get right back to the 2x squared plus 7x minus 4. So when we have a value in front of that ax squared, it's best to rewrite the middle term so that you can use factor by grouping. In our next problem here, we see three terms. We notice that it is not written in descending order, so that's the first thing we want to do is rewrite that. 3x squared plus 4x plus 1. I'm going to rewrite it and see what our factors come up with. So I'm looking at that first term and the last term. I multiply them together to get 3, and I'm thinking of all factors of 1 and 3. Because the 1 is a positive, I want to add those together to get 4, and that does match my middle term of 4. So I'm going to take that 4x and rewrite it as 3x plus 1x. Everything else would stay the same, so in front I have 3x squared, and I have that 1 at the end. Now I can use my factor by grouping. I factor out a 3x, and I get x plus 1. In my last two terms, I can't factor anything, so that's when we rewrite it with a 1. And then I see I have those common terms that fall into place for the factor by grouping. So I could pull those out, x plus 1, and I regroup the 3x plus 1. So again, we can distribute this out and be able to get back to the original problem the way it was presented. So I'm using everything I learned about finding the factors for a trinomial, but I'm also rewriting it as a factor by grouping, which makes my determination of factors much more straightforward. Okay. Let's do the same thing for part C. Again, we need to put it in descending order. 12x squared minus 23x plus 10. And again, I'm focusing on that first term and last term being multiplied. When I do that, it's a very large number, but we're going to work with that. So 12 times 10 is 120. And then I'm listing all the factors, and we're going to have a lot here. So there's a lot of factors, and I'm just going to start with 1. Use your calculator if you have to. 1 and 120, 2 and 60, 3 and 40. 5 and 24. Oh, we missed 4. 4 and 30. They're not in order, but that's okay. Let's see. 6 and 20. Let's see. Does 7 divide into 120? Just using my calculator. It does not. 8 and 15. And 10 and 12. So I think I have them all. Remember, the determination whether you add or subtract them comes from this plus right here. So if the C is a plus, we're going to add them together. So I'm just going to do a quick add of all of these numbers, and I'm looking to match that 23. So if you see it right off the bat, you don't have to do all individually. I can see it's right here. So that 8 and 15 gives me that 23 that I was trying to match. So I'm now going to rewrite that 23 as 8x and 15x. And since the signs are the same, I know my factors will be the same and they're both be negatives. Okay, so following those rules we learned in the last section. So in front I have the 12x squared, and in back I have the 10. I'm now going to factor by grouping. So group the first two and the last two. And first two I can factor out a 4x. I'm left with 3x minus 2. The second two I can factor out a negative 5. And I'm left with 3x minus 2. So this is the part where you want to make sure that you're ending up with these common factors. If you didn't, something went wrong, you either want to back up a step and reverse the order or check your factors. Okay, so that 3x minus 2 comes out. There's only one, it's never squared. And then we're pulling together those factors that are outside the parentheses to form the second factor. So 3x minus 2 times 4x minus 5. Again, you can use the distributive property to check it. Okay, lots of practice for this technique is needed. Okay, so part D, let's look at part D. Again, I'm multiplying the first number and the last number. When I do that, I get 72. I'm listing all the factors, and use a calculator if you need to. 1 and 72, and I'm trying to get two factors that add together to be 17. And if right off the bat you know it, so 72, I think of 8 and 9 pretty quickly, and I know I should be adding them, and it gives me 17. So if you found those factors right off the bat, that's great. You can stop right there. You don't have to go any further. We're taking that 17 and rewriting them. It's a plus on the 12. The signs are going to be the same. It's going to be a plus. So this is going to be 8x and 9x. The front and back factor come down to be 12 and 6x squared. Okay, I now factor by grouping. 6x squared plus 8x, I can pull a 2x out. I'm left with 3x plus 4. Second grouping, I can pull a 3 out, and I'm left with 3x plus 4. Okay, so here's where we stop. We make sure that we have the same factors. I see them. So now I have 3x plus 4, and I'm grouping together that 2x and the 3. Again, we could always make sure this works by FOILing, distributing, combining like terms, and getting right back to the starting polynomial. Part E, as soon as I look at this, there's a couple things that we have to do. First, it's not in descending order, so I am going to put it in descending order. 14x to the 4th comes first, plus 19x cubed minus 3x squared. The next I notice it's not in the format of a trinomial where it should be x squared, ax squared plus bx plus c, which is a kind of hint that I probably have a common factor. I see I can factor an x squared of everything. So now I see that I have that trinomial format that I can then work on my technique with. Okay, so I can multiply the 14 and the 3 together, and then I'm listing out those factors, and this time I'm looking for the difference to give me a 19. Okay, so when we work that through, we can rewrite those factors. So 14 times 3 is 42. We're then looking for two factors whose difference is 19, difference because of that negative. Okay, so the first factor I think of is 21 and 2, and we do see that their difference is 19. So we're going to rewrite this to be 21x and 2x. Because it's a negative, one needs to be a plus. We always put the sign of the 19 with the bigger number, and then we're going to have a minus. So now I'm going to bring down the rest of the terms, minus 3, 14x squared. I'm going to start my grouping, and I can factor out a 7x, which will give me 2x minus 3, and a minus 1, 2x minus 3. And this will give us 2x minus 3 times 7x minus 1. We don't want to forget the x squared is also part of the final answer. So that GCF that we factored out in the beginning, we want to make sure we include in the final step. Okay. Our last problem, our numbers are pretty high, so I do want to make sure that if there is a GCF, I factor it out. So we can use our calculator again. We're looking for the same number that might factor into 27, 72, and 48. So I start with 2, but it fails on 27. So then I'm going to go on to 3, and I do see that 3 factors into all 3 terms listed. So I'm going to factor out a 3 and rewrite it and see if it's a little bit more straightforward of a problem. So we get 9x squared minus 24xy plus 16y squared. Okay, so there's a lot going on in this problem. We want to talk about a couple different things. So remember, we are trying to factor into 2 binomials, and we see it has x's and y's. So we know that the first term produces x's that come from the first position, and the last term is where the y's would fall in those last positions. Okay, now we can multiply 9 and 16 together and work through these, but I want to give you some hints. Whenever you see a perfect square number in this first position and in the last position, so in other words, 9 can be rewritten as 3 squared, and 16 can be rewritten as 4 squared. So when you're working with perfect squares, these are called 9 and 16 in the first and last position, often those are the values that fall in the factors. So in other words, we get 9 from 3 times 3, so I'm going to put 3's in the first positions, and 16 comes from 4 and 4. And then if I look at this sign and follow the rules of above, this sign tells me the factors are going to be the same. Look to this sign to tell you what they are. I'm not going to forget about this 3 that factored out. This goes in front here. Okay, so these are the factors that often work. How do we know they work? Well, again, you can distribute this out and you can combine like terms and you will get back here. You could have also used the technique of rewriting as a factor by grouping, and that would work. You could have also used trial and error to look at all the different factors of 9 and 16 and try and make that work. So again, a couple different approaches. The one thing I do want you to recognize now is that these are the same factors, 3x minus 4y, 3x minus 4y. Anytime we have that, we do want to go that next step and write that as a square. Okay, so this technique of factoring is definitely the most challenging that we will probably do and takes the most practice. So before you go to your MyMathLab homework, you really do want to take the time to get out some blank paper and really work through all of these problems again, even a couple times, to make sure that you understand the process. In section 5.4, we'll be working on 2 new factoring techniques, and they are called factoring perfect squares and the difference of squares. So let's just look at them. When we look at the word difference, to us, we remember that that means subtract. And when we talk about the squares, again, the squares mean that we can rewrite a number as a value squared. So if we go to the side and we review, we know that 4 is a perfect square because it could be written as 2 squared, and 9 is a perfect square because it will be written as 3 squared. 16, 4 squared, 25, 5 squared, and so on. So when we think about 2 squares, we want to start considering if we only have 2 terms and they have squares in the first positions and the last positions that really we can predict their factors a little bit easier. The A's and the B's would fall in the first position, and one of the factors would be a plus and one of the factors would be a minus. If we factor a trinomial and we end up with the exact same factors that we can rewrite as a square, this is called a perfect square trinomial, and we've seen a few of those already. The last problem we did right here, we saw had a repeating factor and we wrote it as a square. Now this problem could have also been factored using a formula. I prefer using the techniques that we've had and rewriting with a square. So we'll cover examples of each of those. Okay, so looking at example A, this is a trinomial. So we have 3 terms and we want to use all the techniques that we've done. Looking at it though, we're seeing that perfect square jump out at us, and we're wondering, is the number in front of the x squared also a perfect square? And we know 1 works out nicely because we can square it. So remember, the guideline was if we have perfect squares in the first and the last position, we can put that 1x and 1x, and the 5 and the 5, and then we look to the sign of the 10 to put the sign. Now the ones in front are overkill and are not needed, but it is technically there, so I wanted to write it out the first time to show you that that 1 does come into play. It's still a value that produces a perfect square. Recognize that the factors are the same. Okay, so we can rewrite that as a square. So this is called a perfect square trinomial. We did not even need to use the formula. I did want to point it out because sometimes you'll see it as an explanation in my math lab, but all the techniques that we've used up to this point will apply. Okay, so part C, I'm going to jump because it's a similar problem. We'll come back to B and C. Again, we see a perfect square. 7 squared gives us 49. And we see a perfect square in 1. 1 squared equals 1. So which means our factors are going to be 7x and 7x and 1 and 1. We look to the signs because it's a positive, the signs will be the same. My 14 tells me what the signs should be. I notice the factors are the same. One more step to write it as a square. So if you're starting with 3 terms with perfect squares, you can expect to have a factor that repeats. Go the final step to rewrite that with an exponent. Notice the next 2 problems, part B and D, only have 2 terms. So with 2 terms and a negative, I'm going to be thinking of the difference of 2 squares. So again, we're working with squares, but we only have 2 terms. Okay, so x squared minus 25. I know 25 is a perfect square. If it helps even to rewrite that 25 as 5 squared. Now, if it's 2 terms, we have to follow the formula that's given to us right here. That says one's going to have a plus and one's going to have a minus. So that means I'm going to have an x minus 5 and an x plus 5. And again, if you're unsure of this, distribute it all out, FOIL it. You'll see the minus 5x and the plus 5x cancel each other. We're left with x squared minus 25. Okay, part D looks similar, but there are a few things that are off here. So first of all, 80 and 45 are not perfect squares. I cannot think of any 2 numbers multiplied together that will give me an 80 or that will give me a 45. Okay, so I want to start thinking, is there a GCF possibly? So I do see that 80 and 45, they should both divide by 5, and because the negative's in front, I'm going to take a negative with it. Always factor out the negative. So the minus 5 comes out, and I have 16a squared minus 9. So here I see, after we factored out the GCF, we do have those perfect squares that show up in the first and the last positions. Okay, so if it helps, remember 16 is 4 squared and 9 is 3 squared. So my factors would be 4a minus 3 and 4a plus 3. And that's a minus 5 in front. These are not exactly the same because the sign, one sign's opposite, so we cannot write them with the square. So remember, two terms, we're going to end up with similar factors and opposite signs. If we started with three terms with perfect squares, that's where the signs and the factors are exactly the same. Let's cover one more of each of these examples. So part E is three terms. It does not appear initially to have any perfect squares. So I'm first going to find out, is there a GCF? So remember, that should always be our first technique. So use your calculator. We cannot divide 2 in, but when we try 3, we do see that 3 works. So I'm going to factor 3 out of everything to get 25y squared plus 30y plus 9. So as soon as I do that, I see that in the first and last positions, those perfect squares pop up. So 25 is a perfect square because 5 squared is 25, and 9 is a perfect square because of 3 squared. So if you have to go to the side and write that down, 5 squared equals 25, and 3 squared equals 9. So we can set up our factors to have a 5 in the first position, and a 3 in the last position, and the y comes in. We look to the 9, it's a plus. We check the sign of the 30, that tells us they're the same and they're both plus. We bring down the 3 that was GCF. The last thing we observe is we do have the same factors. We bring them together with an exponent. So it is 3 times 5y plus 3 squared. We go to part F. It's two terms, so we're thinking about squares. But I do see that we have an extra x in each of them. So the first thing I want to do is factor the x. I get 121 minus 36x squared. So again, use your calculator if you have to, but 121 is a perfect square, and so is 36. So 121 is 11 squared. And 36 is 6 squared. Notice the x appears in the second term now, so when we factor, we have to make sure to account for that. 11's in the first position, and then a 6 and an x in the second position. Because it's a negative, one gets plus, one gets minus. So again, I'm following the guidelines that appeared back here for two terms. One factor is a plus, one factor is a minus. We don't want to forget about that x we factored out front. When we look at this closely, we see that these are not the same factors because they do differ in sign, so we do not want to write this one with a square. Okay, so two special types of factoring that we want to be able to recognize in our factoring techniques. Our next section talks about factoring cubes. Okay, so cubes, notice we have the sum and the difference. The word sum and difference means plus or minus. So we have two formulas here, and these formulas, first of all, I want you to have them in front of you while you're using them. You will be given these formulas on a quiz or a test. So you don't want to have to memorize the formulas just to be able to use them. And they're very similar. There's really only a few differences of the signs. And the way I explain it, for a cubed plus b cubed, the first sign always matches. So the pluses matches or the minus matches. The second sign is opposite. And then the last sign is always a plus. So we're going to be looking to rewrite polynomials that have two terms that can be rewritten as cubes. And if we can do that, if we can group it as a cubed plus b cubed, we simply follow the formula and we substitute these values in. So first let's talk about our cubes, and let's go to the side. So I want to list out some of the cubes that we may be working with. So we'll start with 1 cubed. We know that simplifies to 1. 2 cubed. 2 times 2 times 2 is 8. 3 cubed is 27. 4 cubed. 4 times 4 is 16, times 4 is 64. And we notice we see a 64 right here in the first example. 5 cubed is 125. And we can keep going. You can always use your calculator if you're unsure of a number. You can either use the cubed root on your calculator, or you could simply trial and error 2 times 2 times 2 or the exponent key to be able to match the cubes. So when we look at this first problem here, and as soon as I see the cube on the exponent of the base x, I'm going to be thinking this might be a problem where I can rewrite it to be something cubed plus or minus something cubed. So I see the x cubed, I see the 64, and these are numbers that we should start to become familiar with so that we recognize them when they're in a problem. We recognize the 8, the 27, the 64, the 125. So these are numbers that are jumping out at us. So I see that 64 and I think, okay, that is a perfect cube. I can actually even go as far to rewrite the problem if it helps. And when we do this, we can see that it is taking on the format of a cubed minus b cubed. Actually, I can go to the side and I could say, in this problem, my a is x and my b is 4. So now, if I follow this formula, I'm working on the a cubed minus b cubed because it's a negative. I can substitute all these values in to the formula. So following this formula, it says it should be a minus b. Well, my a is x minus 4, and a squared, so that's x squared, plus x times 4, plus 4 squared. So this first step here, I directly substituted everything into the equation, and then I just want to go back and I want to ask myself, are there any areas that I can simplify? So I'm going to rewrite this, just simplifying anything that can be. Anytime I see x times 4, I tend to rewrite that just to put the constant first, 4x. And we know that 4x squared, 4 squared is 16. So this is as far as we can go. We do not want to distribute it or write it out. Remember, we're factoring. If you did use the technique we learned in chapter 4 to distribute out and combine like terms, you would get back to that original problem. So you can do that as a check. But this is the final answer. Okay, let's go on to the next problem. We see that 64 show up again. It's in the first position this time, and I see a 125, and I also see an x. So again, it may be helpful to rewrite the problem so it's clear how the cubes can be perceived. So 64 is 4 cubed, and 125 is 5 cubed, and then I also had an x cubed. So I have two things happening in the b position. We're still working on the second equation because it has a negative. I think I'm going to go to the side and label just so I'm clear that my a, represented by the 4, is in the first position, and the b, not only does it have a 5, it has an x. Okay, so I'm following the formula. I'm substituting in a minus b is 4 minus 5x. A squared is 4 squared minus 4, plus 4 times 5x times plus 5x squared. Now when I square this, I have to make sure I put it in parentheses because the 5 is squared and the x is squared. I do have a few things that I can simplify here. I can multiply this 4 and 5 together. I can also square the 5 and the x in the last term. So I'm going to go one more step. 4 minus 5x. Oh, I can also simplify this 4 squared. 16 plus 20x plus 25x squared. Okay. So you do get the formulas. You just have to know how to rewrite them and identify what a and b is, and then to also substitute into the equation and simplify. Let's review a few more examples of this technique that we've been using. Part C, I see the cube, so I'm thinking about the first formula that has a plus a cubed plus b cubed. But when I think about 54 and 2, they are not perfect cubes. But I notice they're both even, so I'm actually going to factor out a GCF first and see if I can get it in the form of the cubes. So if I factor a 2 out, I get 27x cubed plus 1. And now we see that we do obtain 27, which is a perfect cube, and 1 is a perfect cube. Okay, so I'm going to rewrite it in my first position. My a is 3x because 3 cubed is 27, and b is 1 because it's 1 cubed. I'm now going to apply the formula, and I'm going to keep that 2 out front. And now I'm going to go into the formula I'm using with the plus, which is a plus b times a squared minus ab plus b squared. So using my a and b here, I get 3x plus 1. Now again, when you have to square something, the whole entire unit goes in parentheses. The 3x gets squared, wrap it in parentheses, minus 3x times 1, or you can use parentheses, plus 1 squared. So anytime you have more than one term, you want to make sure that you're putting it in parentheses. We can simplify here, here, and here. So one more step to be able to rewrite this, to simplify it. So I have 2 times 3x plus 1. So 3x squared is 9x squared minus 3x plus 1. Our last example, 343x cubed minus 1. So we know 1 is a perfect cube. We may not be familiar with 343. We can go to our calculator. We know we went up to 5 over here, so think about 6 cubed, not 343. How about 7? 7 cubed is. So if you'd like, let's rewrite that. This is 7x cubed minus 1 cubed. So our a is 7x. Our b is 1. I'm now going to use the formula above that has a negative, and I'm going to substitute into a minus b. So a is 7x, b minus 1. A squared is 7x squared plus 7x times 1 minus 1 squared. Simplifying those second terms, 7x squared, remember 7 squared is 49x squared plus 7x minus 1. So we're all simplified here, and these are our final factored answers for the sum and difference of cubes. In section 5.6, we're going to take all of the factoring strategies we've learned individually, kind of mix them together, and talk about a general strategy for factoring. So the first thing we've mentioned a few times is that you should always look for a greatest common factor first. Okay. After that, you want to start looking for things like, are there any perfect squares or perfect cubes? How many terms are in each of them? Remember, if we had 3 terms, that's where we used our factoring a trinomial. If we had 4 terms, our technique was factor by grouping. If we had 2 terms, we had the squares or the cube formulas. Okay, so we really want to think about how many terms there are there any perfect squares or perfect cubes? What should our technique be? Step 3 says factor completely. That means there may be problems, and we're going to do some examples now where you have to use several different factoring techniques in one problem. And 4, remember that you can always check your answer by distributing and multiplying out to get back to the original problem. Okay, so we're going to look at some problems that are challenging, that use multiple techniques, but I think we'll pull all our factoring together. So problem 1, 4 terms. First thing we should always do is look for a GCF. So I look at every single term. First I'm going to ask, is there an X in every single term? In the first 3 terms there aren't, but it's missing from the fourth, so we cannot factor an X out. And since our first term doesn't even have a constant on it, we can't factor a constant out. So the next thing I'm going to say, okay, how many terms is it? Well, it's 4 terms. Remember, our technique for 4 terms is grouping. So I'm going to factor again the GCF, but by grouping the first 2 terms and the last 2 terms. So when I look in the first 2 terms, I see I can factor an x squared out, giving me x minus 11. Okay, so now I'm looking at the next 2 terms. Now the next 2 terms have very big numbers, but the hint should be if we factor by grouping, we're hoping to end up with an x minus 11. Now the only way to get that would to be divide 1,331 by 11 and see what we get. And if you put that in your calculator, we get 121. So I'm going to try to factor out a 121, and I'm going to take the negative because of this negative sign right here. So I'm going to factor out a 121. So 121x divided by 121 is x. 1,331 divided by 121 is 11. So although there are bigger numbers, there are hints to set us up, and this is exactly what we were looking to happen, that we get that same factor of x minus 11. Now remember, in factor by grouping, we want to pull together these terms that are out front into its own factor. So that's where that x squared minus 121 comes from. Okay, so we factored this successfully with factor by grouping, but I want you to look at this very closely and ask yourself, is there anything else you can do? Can you factor any more? So when I look at x minus 1, it doesn't have any squares, it doesn't have any cubes, and it doesn't have a GCF. So I don't think there's anything else I can do. When I look at the pink, the x squared minus 121, it doesn't have any GCF, so I can't do that. But I'm seeing that there are squares, x squared, and 121 I know is a square. So I'm thinking it has 2 terms. I can actually think of this as, I'm going to rewrite it, x squared minus 11 squared. Okay, so if you want, I'm going to rewrite this as x squared minus 11 squared, because 11 squared is 121. And I know that if I have the difference of squares and it's a negative, has to be a negative, that's the key, that this factors into x minus 11, x plus 11. And I still had this factor of x minus 1 that I wanted to bring down. Okay, so we had, I'm sorry, this is x minus 11. So we had an x minus 11, and then we added another x minus 11, and then an x plus 11. So now I should recognize that these 2 factors are the same. So we want to write that as a square, and then I'm going to bring down that x plus 11. So here's a problem where we use several techniques. We first factored by grouping. I then factored the difference of squares. I then recognized that I had 2 binomials that were the same that I wrote as an exponent. So 3 techniques here. Final answer has 3 factors. 1 is a repeat, so I'm going to square it. Okay, part B, our next problem. We're always looking for a GCF first. I do see that I can factor a 2 out of each, and I can factor an x out of each. So 2x, and I'm left with x to the 4th minus 16. So this is 2 terms. It should be jumping out at you that 16 is a perfect square, and also x to the 4th is a perfect square. Watch how I rewrite this. I can write 2x, and we learned in chapter 4 that we can have a base with an exponent raised to another exponent. So let's go back and review that. X squared raised to the 2nd power. The power rule says I multiply them by itself together to get x to the 4th. Okay. So now this x squared minus 4 squared can be broken apart into x squared minus 4, x squared plus 4. Okay, and you should be recognizing that x squared minus 4 is the difference of 2, which can also be broken down into x minus 2, x plus 2. 2x is still out front. And the x squared plus 4, let's talk about that. So even though there are perfect squares in the first position and the last position, because it doesn't have a negative, it cannot factor any further. So anything with a plus is actually prime, does not factor any further. So that's an important point. You don't want to spend a lot of time working on something that you think it should factor. If you have two terms and they're squares and it's a plus, it's prime, it does not factor. If it's a negative, it does break down. Let's look at two more problems. Always looking for a GCF first. I look at these four terms. I do not have a GCF. Since it is four terms, my first approach is going to be grouping. I'm going to group the first two and the last two. I can factor out an x squared. I get x minus 25. Last two, I can factor out a negative 4, and I get x minus 25. This is what I was looking for. I want to pull that factor out. Regroup the other factors, x squared minus 4. So factor by grouping is done correctly, but we should recognize we have an x squared minus a 2 squared, and it is a minus, so it can break down further to factor. So the x squared minus 4 factors into x minus 2, x plus 2. Don't forget to bring down that x minus 25 that's in front. Now we are what we call completely factored. I don't have any repeating factors, so I really don't have anything else that I can rewrite with an exponent. This is the final answer. Our last problem is three terms. We first want to look for a GCF. I see that I can factor an x out. My lowest exponent is a 4, and because of the leading term being negative, I'm going to factor a negative x to the 4th. When I do that, x to the 6th divided by x to the 4th is x squared. And notice the sign change because I divided by a negative. My next term is going to be a negative 4x plus 8. So notice the three terms that remain in parentheses do take on the format of a trinomial, so I definitely want to think about factoring a trinomial. Our approach was to take the 8 and 1 and multiply it together, and think of all factors of 8, which are 1 and 8, 2 and 4. Because of the plus, I'm going to add them together, and I'm going to look to match that 4. And do you see what happens? Although we have two possibilities, neither one of them actually match that middle number. So we're looking to match this 4. So this technique actually doesn't allow us to go any further. We tried, but it does not. So although it is in the trinomial format, the polynomial we were trying to factor is prime. Okay, we don't want to say the whole thing is prime because we were still able to factor out the GCF. So the final answer using just the GCF would be this. Okay, so we always have to try some other techniques, but they won't always allow us to progress. The last section, section 5.7, we're finally going to bring the equal sign back. We're going to use everything we learned about factoring, and we're going to set it equal to 0 and understand that we can now find solutions and what do they mean graphically. Okay, so the ax squared plus bx plus c is actually known as a quadratic format, and if we set that equal to 0, then we can use the principle of zero products that says take your factors and set them equal to 0, allowing you to solve for up to 2 solutions. So let's show you what that looks like. In our first example here in part A, notice that we already have our factors completed. If we kind of glance to the next problem, we see that work is not done for us. But if we've already factored and we're set equal to 0, that's the key, then we can take those factors and set up mini equations, set each of those equal to 0. And then we can solve by subtracting 1, and we get our solution of -1 and our solution of 8. So finally the equal sign is back, finding our solutions, and we get to solve for x again. In part B, you can see that it's not factored. The condition, it must be set equal to 0. If it wasn't set equal to 0, we would have to do that. We would have to move terms from the left to the right side of the equal sign. So now we're going to use all of our factoring techniques to be able to factor a trinomial. And in front of the x squared, it's 1. This was, the little bit easier of the type where we can simply set up our factors. We know there'll be an x in the first position. I'm thinking of all factors of 21, whose difference, because it's a negative, is 4. So I immediately think of 7 and 3, and the difference of 7 and 3 is 4. I'm going to look to the 4 for the sign. It's a positive. Always put the same sign with the bigger number, which makes this the negative. Since it's set equal to 0, I can now set each individual factor equal to 0, and I can solve to get x equals -7, add 3, and x equals 3. So the equal sign is back. Part C, notice here's a problem where it is not set equal to 0, so I have to work for that. I'm going to take the 49 and move it. The opposite of adding 49 is subtracting. I'm going to do it to both sides. Get 4t squared minus 49 equals 0. And now I'm thinking about all those factoring techniques I've learned to apply to my 4t squared minus 49. I notice it's 2 terms. I also notice the 4 and the 49 are perfect squares. So if it helps to rewrite the problem as 2t squared minus 7 squared, those are my perfect square values. That will help me factor it. I have 2t minus 7 and 2t plus 7. I could then set each of them equal to 0 and solve. When I divide by 2, I get t equals 7/2. I could do the same thing here. I subtract the 7. I divide by 2. And I get t equals -7/2. So the first time we're encountering fractions when we solve, but that's okay. It's really just in the last step that we're dividing to do that. In part D, we have factors, but it's not set equal to 0. So what we need to work on is moving that -16 to the left-hand side, and then we're actually going to have to distribute out to incorporate that -16. So I'm going to do a couple different things here. I'm going to distribute here to get x squared minus 7x plus 1x minus 7. And then I'm going to add 16 to both sides, which would bring the 16 over, and then set it equal to 0. I'm then going to combine like terms, so I have x's that can be combined, and I have -7 and 16 that can be combined. So I have x squared minus 6x plus 9 equals 0. I can now factor, and I have a perfect square of 9. Factors of 9 are 3 and 3. They do add to be 6. So x minus 3 and x minus 3 works. Here we have 2 factors. We don't necessarily have to write it as a square, because what we're going to do is take each of these factors and set it equal to 0. When I do that, I get x equals 3. I could do that twice, but I don't really have to. It's repetitive. It's the same answer. when we list our answers in MyMathLab, there would only be one unique solution. So I'd only need to list that one solution. Looking at our last example, x squared minus 3x minus 4 equals 0, we're asked to find the solutions and then talk about what it means graphically for those solutions. So we're going to use the same approach. We check and make sure it's equal to 0. It is. This is a trinomial, 3 terms. It has a 1x squared in front. So I'm going to take the approach where I'm factoring x and x. I'm looking for all factors of 4 that their difference is 3. So that's because of the negative. So I'm going to use 4 and 1 because I know the difference of 4 and 1 is 3. I'm going to look to that middle term to tell me what the sign of the larger number should be. So the larger number gets a negative and the sign should be opposite. So this one is a positive. I'm going to set each of these factors individually to 0 and solve to get x equals 4. And this will give me x equals negative 1. So we know what the solutions are, but we've been asked what that means graphically. So when we have solutions, this 0 that everything gets set to is actually the y value on the graph. So I can take the x value 4 and pair it with the y value of 0. I can take the negative 1 and pair it with 0, which means this graph will pass through the points of negative 1 and 4. And this is the first time that we're going to introduce the graph of a quadratic. So a quadratic was mentioned earlier, has the form of ax squared plus bx plus c. And the graph of a quadratic, it looks like a U. It's actually referred to as a parabola. And the U opens up if the value in front of the x squared is positive, and it opens down if the value in front of the x squared is negative. So we know a lot more about the functions that we've been working with, and we can draw that U, which would go right through those 2 points that we just solved as our solutions. And remember, these 2 points are called intercept points because they touch the x-axis and they have 0 in the y position. Okay, so this is a parabola that has x-intercepts at the solutions. And finally, we want to talk about the last page, which is a factoring reference sheet. And I think this is a good summary when you're factoring. Remember that the first technique you should always do any number of terms is the GCF, try to factor out the greatest common factor. And then from there, you really want to think about how many terms. So if it's 4 terms, your technique should be factor by grouping. If it's 3 terms, that's the format of ax squared plus bx plus c. We call that a trinomial. We rewrote that as a factor by grouping, and then we checked it using FOIL in the distributive property. Then we have our 2 terms. Our 2 terms can be split into the squares and the cubes. So if it's a squared with a negative, remember it factors, but if it's a square with a positive, that's prime. Okay, and then we have the 2 cubes. Again, you'll be given these formulas on any problems. If you remember the formulas and how to use them, then it should be pretty straightforward. You will not have to memorize these formulas. And finally, our perfect squares and perfect cubes. So these should all be numbers you're familiar with. I have them written out here, so for a reference, these numbers should be jumping out at you when you're working on problems that involve squares or cubes. You can always use your calculator to check it, but you should be familiar with these numbers because it will help you recognize the technique earlier.